to this session. And this symposium is about new challenges in computerized adaptive testing and potential solutions, as well as innovative applications of CAT. In fact, it was my colleague, David Weiss, who asked me to put together a symposium. So I reached out to my colleagues, friends, and my advisor. And I feel very grateful that they all agreed to participate. So this symposium can never be put together without their contribution. So there is a rumor around here that Dave never travels, but this is not true because he does travel once a year from Minnesota to Florida. But anyhow, for those of you who miss him here, in 2 years, this conference is going to be held again in Minneapolis, so you will see him there. Since we have 5 presentations today, so it's a full program, so without much overdue, I will introduce the first presenter, Xue Zhang, and her topic is about estimation in computerized adaptive testing when missing at random is not satisfied.
Good afternoon, everyone. I'm Xue Zhang from Northeast Normal University. The topic I will present today is the atom calibration method for computerized adaptive testing when the missing data mechanism is non-ignorable. It's the joint work with Dr. Chun Wang from University of Minnesota and Dr. Jian Tao from Northeast Normal University. Oh, sorry. Let me give you a brief overview. First, I will show you the background, and then the detailed method will be presented at the second part. A simulation study will be conducted to illustrate the performance of the proposed method, and we will end with some conclusions. The CAT framework we use here consists of 2 parts. The adaptive testing part and the atom calibration part. In the first part, the examinee administered the initial atoms from the old atom pool, and we estimate theta based on the responses of the initial atoms and the diagonal convergence. If it's neither convergence nor matches the max iterations, a new atom will be selected and administered from the old atom pool based on CTAT. After the first part is fulfilled, a new atom will be selected from the new atom pool based on the current CT estimate, and the corresponding parameter estimations is similar to the first part. The test will end when it matches the max iteration. For the purpose of the atom bank maintenance and management, atom replacement is essential to permit retiring or exposed all obsolete atoms over time and replacing them with new atoms. When the atom response new atoms are collected with adaptive testing or multi-stage testing, the adaptive atom selection or state routing is based on examinee's interminability estimations. In other words, the missing response on unselected atoms depend on the latent trace. We can consider it as missing. Hence, the response missing at random assumption made by the traditional online calibration methods is like validated. As a result, the missing assumption will lead to erroneous atom calibration. Rush model is used here as the measurement model. YIG is the binary scored response of examinee I for the G selected atom. Set I is the latent trait of examinee I. BIG is the difficulty parameter of the G selected atom by examinee I. D is the scaling constant. When it equals 1, the boundary function is the logistic model, and when it equals 1.7, the function is a logistic approximation of the normal given model. Here we set D equals 1. And the EAP algorithm is used to do scoring. In equation 2.2, Ly given theta is the likelihood function, and pi theta is the prior PDF. D-optimality is used as the item selection criteria, which is based on the facial information. I seat here equals D squared times 1 point pi seat times pi seat. Before to introduce how to calibrate the item pool, some notations need to be described here. While ops I denotes the set of observed response of examiner I, while miss I denotes the set of missing response. Delta denotes the set of unknown item parameters for new items. Gamma op denotes the known item parameter for operational items. Mu and sigma denote the mean and variance of theta. Mi denotes the missing data indicator of examiner I. M equals 1 denotes observed, otherwise M equals 0. N denotes the sample size, and G denotes the test size, which equals G old plus G new. EM algorithm is used to calibrate the item pool. In each step, we calculate the conditional expectation of the log likelihood of the complete data Z with respect to missing data Z miss, given the observed data Z obs, and the current parameter estimation at the tth iteration, delta t, mu t, and sigma t. In M step, we will find the parameters that maximize the conditional expectation of the log likelihood function from each step. In each step, we define the conditional expectation of log likelihood as a Q function. It's an integration with respect to y miss and theta. The log likelihood can be divided into 3 parts. The first part is the log likelihood of the observed responses. The second part is the log likelihood of theta, and the third part is the log likelihood of the missing indicator. The corresponding 3 parts of Q is denoted as Q1, Q2, and Q3. In equation 2.6, U here denotes all the response patterns of unselected item, and K denotes the number of nodes. If the responses are missing at random, Q3 equals 0, and PQK giving Y ops Y, delta T, mu T, sigma T, and gamma op can be expressed as equation 2.7. On the other hand, if the responses are missing not at random, PQK giving the rest parameters can be expressed as equation 2.8. We can see that equation 2.7 is a specific case of equation 2.8, which restricts PMI given QK and delta T to be a constant. So we will introduce the missing mechanism model next. As the seat estimates changed a little after adding new items, we assume independence between the MIGs. The binomial model is chosen as the model for missing mechanism. And the light phi denotes the missing mechanism parameter that we can obtain the PM given seat delta and phi. When the rush model is considered as the measurement model, according to the item selection mechanism, the absolute difference between seat and B is the smallest will be selected. The probability of missingness can be expressed as equation 2.10. And the figure 2 shows the probability of the missingness, which can be treated as a function of seat minus B. It's an illustration of the missing mechanism in equation 2.10. We set phi equals 0.3 and 0.45 at the example. In M step, we can obtain the first order derivatives of Q and then set them to be 0. Mu and sigma has closed form solutions. The MATLAB package FSO is used to approximate the solution of BJ. As phi denotes a standard deviation, the MATLAB package LSQ nonlinear is used to approximate the solution of phi, with lower bound 0.0001 and upper bound 5. In simulation study, there are 9 conditions and 100 replications are done. Rush model is chosen as the generation model and the calibration model. The number of odd atoms is 20 and the number of selected atoms is 6. We join the latent tree from a standard normal distribution. 3 different levels of sample size and 3 different levels of the number of new atoms are considered. In other words, there are 3 levels of the missing proportion. And we join B old from a standard normal distribution. And B new is increased from -2 to 2, which is generated based on G new. And the initial values of B new is also based on G new. And the initial values of mu, sigma, and phi is set to 0, 1, and 0.45. Root mean square error and bias are used to summarize the parameter recovery. For B estimates, MNAR can outperform the MAR when the missing proportion is 40% and 90%. But when the missing proportion is 60%, the basis of B from B from MAR is a little smaller than those from MNAR. For seat estimation, the RMICs are similar, but the bases from MAR are all smaller than those from MAR. And MAR can recover mu and sigma better than MAR. That may be because of the operational items and the misspecification of missing data mechanism model. Actually, I also confused about it, and I apologize here. I'm still working on figure out the reason. And the phi estimates are also reported here. Next, I will show you the box plots of B new. Figure 3 is for small sample size. The first row is for small G new. Second, for medium G new, and the last row is for large G new. When the missing proportion is 60% here, we can see that MNAR is hard to recover B new with negative values. Well, actually, it's the worst. That's the reason why when the missing proportion is 60%, the bias from MNAR is larger than that from MAR. And figure 4 is for medium sample size. The result is similar to figure 3. Figure 5 is for large sample size. The result is similar to figure 3 and figure 4. According to the simulation study, the responses missing mechanism and the CAT framework was missing node at random. And for B estimates, the MNAR assumption outperformed the MAR assumption. As the effect of sample size was negligible, we recommended that when to calibrate the new atom pool, we can divide the large atom pool into some small subgroups and link them to the same scale after the calibration. In this study, the MAR assumption can recover seat better than the MNAR assumption. I think maybe only in this study. And in future, we will consider more simulation conditions, and we will compare different missing mechanism models and the effects of different initial values. Finally, we will extend this study to 2PL models and the multidimensional models. Thank you for your time.
I'm being disappointed by data not being useful enough. Could you explain that?
Sorry, you mean I said the misspecific of?
Oh, I'm disappointed by the data not
Sorry, do you mean the? I say the misspecific of missing mechanism model?
Yeah. Oh, I do understand the missing mechanism model.
Oh, yeah.
Why are the data, the calibration data?
Because here we used the optimality as the item selection criteria. It's based on the facial information. I will find it here. And the facial information of the rush model is this step. When the seat manner speed, let me see how to say. When the seat manner speed is nearby 0, the missing probability is nearby 0. And if the seat manner speed is larger, the probability of missing will be larger. So we model the missing mechanism like this.
That I do understand the probability of potentially. But there's no missing data. This would hold any test assembly need to receive data that's missing all the time.
So I think her idea is, so in online calibration setting, you assign new items based on theta estimates, and theta is sort of latent, so it's more sort of missing. If you assign new items based on this missing data, which is theta here, then this missing had been something.
Data estimates are based on other responses, not on the response to
Yeah.
calibration. You don't have a response to calibration.
Right.
How can it be missing all the time?
Theta could be updated from both the operational and potentially new items.
Let me try another question kind of related to the same thing. How are these items being administered to individuals? How is an item to be calibrated stuffed into the adaptive system? Does it appear randomly to a person who is taking other items? Or does it appear non-randomly with some sort of preliminary estimate for the information?
Because when it's a simulation study, and when we generate the data in the second part, the calibration part, we will estimate seat head in each step and then choose the new items based on the seat head.
I think in the simulation, because we assume we know
The true, yes.
new items, so then we use information based.
Yeah.
So the item has a set of parameters associated with it. And so it's being administered with that set of parameters. So it's a very truncated range of individuals who are taking it. But it might not be truncated in the right place because you have, you're trying to get the calibration for that item.
Yeah.
So the data is missing, not at random.
Yes.
Okay.
Thank you for your question.
All right, so we will move on to the second presentation.
Okay. I'm Yin Honghe. I come from Beijing Normal University, and the topic of my presentation is online calibration, and the title is an ability estimation based on set point approximation and its application to online calibration. And in this presentation, firstly, I will make an introduction to about what is calibration, and then the method used in this research is introduced. Next, the simulation studies with the results and the conclusions will introduced. And we know after a period of time, some items may unsuitable to use. That new items should be developed to substitute the unsuitable ones. And there are some ways for calibrate the new items. In tradition, we may recruit volunteers to calibrate new items. And in contrast, we may see the new items to the test takers during their adaptive testing sessions. And in this way, we call it online calibration. And it is cost-effective and more reliable. In general, there are two important aspects of online calibration. One is online calibration design, and the other one is online calibration method. Online calibration design defines the way of choosing examinees for a given item, and the online calibration method concerns how to estimate the new items precisely. Here we focus on the online calibration method. And there are several online calibration methods have been proposed, such as method A, method B, OEM, MEM, and MC method, and so on. Among all these calibration methods, method A is the simplest and could give acceptable calibration precision. So here we focus on the simplest method A. And there are some advantages of method A, such as it is simple and easy to calculate. And the CD CAT version of method A outperformed the CD CAT version of OEM and MEM. In addition, the multi-dimensional CAT version of method A recovered the item parameter accurately. And however, the method A treats the estimate ability values as the true ones. Thus, the estimation error may yield inaccurate item calibration. So one way to improve method A is try to estimate the ability parameter precisely. And there are some ways to estimating for estimating ability precisely, such as correcting bias for the obtained estimates, or preventing bias during the estimation process, or taking the measurement error into consideration. And different from all of this method, in this research, we try to incorporate auxiliary information to estimate the ability precisely. And in addition, the auxiliary information used in this research is the prior information and the distribution information, which I will discuss later. And in this research, we employ the two-pair model as the RT model. Thus, the PDF of a text taker's response belongs to the one-parameter exponential family and can be expressed as Formula 2. Then the distribution of theta I hat can be approximated by the set point approximation, where theta I hat is the ML estimator of the true ability. And then the PDF of the true ability conditioned on the estimated ability estimator can be expressed as the equation 4, where in this equation G theta I is the prior distribution of theta I. Thus, we propose a new ability estimator and can be expressed as Formula 5. And in this, and we name this new method as MAE with the set point approximation method. And please note that this new ability estimator is obtained by taking full advantages of the distribution and the prior information, and thus it is expected that the new ability estimator is more accurate than the MAO estimator. And we also apply this new ability estimation method to the online calibration, and we combine this new method with the original method A to improve its performance and propose a new online calibration method, and it is referred to as the MAOE setpoint approximation method A. And this is the general framework of this new online calibration method. First, we should obtain the MAO ability estimates, and then we should employ the new ability estimation to estimate the ability parameter and obtain the new ability estimates. And step 3, the new estimates should be treated as the new ability values. And finally, the case new item is estimated by solving the following log likely equations. And in addition, simulation studies is conducted in several conditions, and we choose 3 levels of test length, 3 levels of sample size as the simulation conditions. And the new abilities are drawn from the standard normal distribution, and the item parameter vector are drawn from the truncate bivariate normal distribution. Then we choose the maximum feature information as the item selection method, and the random online calibration design is used to assign the new items, and each new item is answered by the same number of examinees. In addition, to compute the integral in the new ability estimation method, the adaptive Monte-Carlo integration is employed. And we also choose the Pearson correlation coefficient and the root mean square error, the bias, and the average weighted error difference as the evaluation criteria. And this is the result and conclusions. Table 1 shows the ability estimates under different experimental conditions. And in this table, the original MAO ability estimator is denoted as theta hat, and the new ability estimator is denoted as theta SA hat. And from this table, we can see that larger test lengths generate smaller RMSE values and smaller absolute bias values and higher correlation coefficients. And compared with the MAO estimator, the new estimator generate smaller RMSE values, smaller absolute bias values, and higher correlation coefficients. And this is the figure 1 shows the results of RMS values of the estimated parameters A and B for test length 30, and this is for test length 40, and figure 3 shows the result of test length 50. And from all of the figures, we can show that as the sample size increase, the RMS values decrease strictly. That is, the larger sample size calibrates items more precisely, which is known to us. And And moreover, the new online calibration method produces smaller RMS values, and the extent of the improvement decreases with the increase of test length. Table 2 shows the results of different online calibration methods for test length 30. And in this table, SA denotes the original method A, and SAMA denotes the new online calibration method. And this is for the result of test length 40. This is for the result of test length 50. And from all of these tables, we can show that we can know that compared with the original method A, the new online calibration method generates the new online calibration method generates smaller absolute bars in almost all conditions, and the AWD values is smaller than the original method A in all conditions, and the correlation coefficients also show that the new online calibration method is better than the original method A. Thus, we can draw the conclusions of this research. And first, for the 2PAO model, the distribution of the person parameters MAO estimator can be precisely approached by set point approximation method. And second, the new ability estimation method has a better recovery for the person parameter than the original MAO estimation method, especially for the extremely ability values. And the new online calibration method outperforms the original method A under all experimental conditions, and the degree of improvement peaks at the largest sample size with the shortest test length. Okay, thank you. Okay, thank you.
Thank you. Our third presenter is Xu Wang from University of Georgia.
Good afternoon, everyone. Today I will present the computerized adaptive testing with response revision. So actually, we started this project in 2015, and then we really had a very hard time to convince people the methodology we propose here might be a useful option. So I really hope I can have longer time to talk about the methodology. And so part of the work I talk about is collaborate with Dr. Hua Chan and Dr. Georgia Flores when I was in Urbana-Champaign. And then after I find a job at UGA, I had some new development, and also I saw there are some challenges I haven't totally find a solution. So I would like to share with some of my thoughts and maybe some suggestions from the audience. So first is about like always why we want to have response revision in CAT. And I think as a student like myself, about like 20 years, from test takers' point of view, I think we just want to provide them a more friendly test-taking environment. I remember 2 years ago, Dr. Chris Han from GMAC have the keynote in IACAT conference, and where he showed they conduct a survey to ask students from 5 countries about their feelings regarding response revision in CAT. And then I believe most of the students, they just prefer this option in adaptive test. And then we do observe the response revision in the computer-based testing environment. Actually, it is adaptive, but it's partial adaptive. It is from the MST test. And then we observe about like 70% students revise about 17 questions out of 90. And for the same question, some students even revise multiple times, because MST allows students to revise response within a stage, but not across different stages. And then there are some studies in both linear test, paper pencil test, and also in computer environment. We do observe the answer. Most of the answer change are from wrong to right. So which means if we allow them to go back to revise, they still may be benefit from this process. And another thing, like from as a psychometrician, we also consider about whether we can gain by allowing them to go back. Can we improve the estimation accuracy or not? So we think that if we allow them to go back to revise the mistakes which do not reflect their true latent trait, this can help us to reduce the measurement error. So in order to illustrate this idea, I just conduct some simulation study. So here we have an item pool with 255 questions, and then there are multiple choice questions, but we calibrate with a 2-parameter logistic model. So this is item pool we got. So this is not a good item pool. Because most of the difficulty parameters are range from -2 to 0, and not that many items for the no ability examinee or high ability examinee. But this is just an example we use. And then we first do a simulation for a standard CAT where response revision is not allowed, and we assume students don't make any careless mistake. So everything follows the 2PL model. So this is a bias we can get for students from -3 to 3, and then for each ability point, we simulate like 5,000 test takers. So, so as we can see, this is quite expected because not many items for the high ability examinee. So that we have relative larger positive bias here and some negative bias for the low ability examinee. So this is quite expected. And then we do some simulation. How about in this situation, there is one student, for students in the ability range, they make one mistake in the early stage of the test. So early stage, we have 40 questions. So early stages, we simulate their mistake during the first one and the first 10 questions. And then when we simulate a mistake, we pick the items they should answer it correctly. So which means based on the 2PL model, they probably have probability 1 to answer, close to probability 1 to answer this item correctly, but we just switch their response from 1 to 0. So in that case, we try to mimic some situation. They made a mistake not due to their latent trait. So we can see that if in that situation, just one mistake in the early stage, the bias, so this is 0. So for all the students in the ability range, they are negative, their bias is negative. So they are underestimated if they have one mistake. So if they have 3 mistakes in the early stage of the test, then the bias become larger. So they are, for students have a true ability at 3, they might just have like 1.5 as ability estimate. So this is kind of reason we want to consider about response revision. We think that the mistakes not reflect their true latent ability may cause very serious underestimation problem. And especially in the early stage, the students, they might be very nervous. They're not familiar with the testing environment, and some warm-up effect, so it's very easy for them to have such kind of mistakes. So that's kind of motivation for us to think about, can we have some methods to allow them to revise response? And then why it is very difficult to incorporate the feature in CAT. I spent a long time to do the literature review, and then this is a challenge I summarized, maybe not very complete, but the first one is we think maybe it is lack of some statistical foundation. So basically, there's not existing literature to discuss about, like statistically speaking, whether the less optimal item will be selected if we allow them to go back. So there are some conjecture in psychometric field for a long time. People think if we allow them to revise, and the less optimal item will be selected. And then, but this question actually can be answered by analyze the asymptotic property of the ability estimator. And the second one is, the second challenge is how to deal with the potential test-taking behavior. So to answer the first question, we always have to assume something is true, like assume the response follow the model. But the second question is how about the response does not follow your model? Because students, the behavior, we cannot control. When allow them to revise, they might have some additional very abnormal test-taking behavior. So how can we handle that? So basically, we want to investigate whether our proposed design is robust for different test-taking behavior. Maybe that's too ambitious, but under some situation, whether the design is robust, and whether this is fair for students, and whether, how about the test security? So I think this is the two challenges we have to deal with. And then we have some question, we already have some answer for the first challenge, and for second challenge, that's still some ongoing work. And so in order to answer these two questions, we need to figure out how to update the student's ability estimation when response revision are allowed. So here I just provide an example. Just think about we have multiple choice format questions. And then if some students really revise some response, then for some item, we can collect more than one responses on the item. And I call it as the response pass. So when we update student ability, then we have two possible choice. The first one is maybe we just use the most recent response to each question. I think this is a quite natural and traditional way in the paper pencil test. So we don't care about what you answered before, but just the final answer will be counted into your final ability estimation. And the second one is how about we use the whole response pass? So that is because now the computer can easily record students' attempts to different questions. So we can also possibly use all the responses to each question and update their latent ability. Okay. So based on this two point of view, then there are two types of ability estimators. The first one, I give the name as a fresh estimator. So basically, this estimator only uses the most recent response to each question and update adaptively during the test process. And I believe, if my understanding is right, most of the modified CAT with response revision design, they use this approach. And then the second one is estimator using all response data. So this is actually our proposed methods when we're starting the project. So basically, then if we use all the response data, we need to figure out how to model the initial response, and how about any subsequent revision. And then most recently, we proposed a model-based approach to answer these two questions. So for the initial response, we just choose a standard IRT model. And then to model the revised response, we actually didn't propose any new model, still based on the original item response theory model, but we just do some math here. So we impose some statistical assumption about given their current response, what's the probability for they change to a different response. But all this probability are calculated based on the original IRT model. And of course, we also impose some assumption for their decision to switch. Maybe I don't have enough time to give all the details, but I would like to discuss after the presentation about the assumptions. So in order to introduce the methods, here are some notation. So consider at time t, the number of, I use RTI to denote the number of times the item I has been revised, because they might revise multiple times. And then if this is equal to R, then we can have a response pass for this item I. And then I just use DI to denote item parameters for item I. So here we didn't specify any particular model, just any reasonable IRT model might be used. And then let's first consider about the MLE in the standard CAT where response revision is not allowed. So this is a score function based on the likelihood, from the data until this time. Because now response revision is not allowed, then all the data is just the first attempt to each question. And MLE for theta is defined as a root for the score function equal to 0. And for the fresh estimator, it's quite straightforward in order to get an estimation. You can just change whenever they revise the response. You can just replace their previous answer with the most recent response. So basically, you change each time when they revise, you update this X for the item I. So that's a fresh estimator. So how about our proposed estimator using all response data? So we actually, based on different modeling assumption, we have two types of estimator. The first one is called conditional estimator, and second one is equal weight. So what is this conditional estimator? In general, we still have a score function, but now the score function has two components. The first component is from the initial response. So this one can be easily obtained based on the IRT model you choose. And then the second one is a conditional score function. It's actually based on our assumption about a modeling assumption giving their previous answer, what's the probability for they switch to a different answer. So we have the conditional score function. And then we use all the data they revise or their initial response during the process. And the theta is defined as the root when this equal to 0. So that's a conditional estimator. And then equal weight. So equal weight is kind of, if we read it down in this way, then it can be easily understand for each responses in the response path for the same item, we give them same weight. So actually, there are some statistical modeling there which result in the final score function in this way. And so in general, we have two types of ability estimator. Then after we propose ability estimator, we need to, so here is kind of a summary. We actually can summarize these three ability estimator by using this general form. Then it becomes how can we determine the weight for the initial response and any subsequent revision. For the fresh estimator, they only give the weight 1 for the most updated response, and then all the previous responses at 0. But you have to update this during the test process. And for the equal weight, we just give the same weight for all the responses during for the same item during the test. And the conditional estimator, we give the weight 1 for the initial. So initial carry the largest weight. And then for any subsequent revision, they have the less and less weight based on the statistical model. And then based on the three different ability estimator, which implies different revision rule. So for the fresh estimator, theoretically speaking, we don't have any restriction. So you can just go back to revise anytime, and you can use any reasonable IRT models. And then for the equal weight, because of our modeling assumption, we have to restrict on the number of time an item can be revised. Because now we use all the responses associated with this item, we don't want to count the same response multiple times. So that's why we have to restrict on the number of time an item can be revised. And for the equal weight, it can be used for both polytomous and dichotomous items and with corresponding models. And then the conditional estimator, they also have the restriction on the number of time an item can be revised. And this is only for polytomous items. Okay. So this is an assumption implied and then for the ability estimator. Then we actually investigate the first question. So what is the statistical guarantee for the ability estimator we propose? Of course, we have to assume some regularity condition, of course, inflate item pool. And then here, if we want to get consistency, the item selection method actually does not really matter. So you can choose any reasonable item selection method. But if when we talk about symptotic distribution, then we choose the maximum feature information as the approach. And then so here this is very interesting, like when the number of revision is relatively small compared to the testness. So basically, students don't revise that many items during the test process. Then for the conditional estimator, we can have when the testness goes to infinity, then you can have a asymptotic normal distribution, and then we can find a asymptotic variance, which is still the inverse of the test information. Okay, so of course this is some situation, very idealized situation, but we can treat this as a baseline. So this is the best performance you might have. So this is for the conditional estimator. And then for the equal weight. So equal weight is even more interesting because in this situation, we can even have higher estimation efficiency compared with the standard CAT, where response revision is not allowed. Again, here we have to assume everything follows the model. Okay, when we talk about statistic property, because now we have more data, then your information is larger, and then the reverse is smaller. So in this situation, you can have even better estimation efficiency. So how to understand this statistical results? We use some numerical analysis, some simulation to actually verify our statistical analysis. So here we consider dichotomous model, 2-peer model, and a polytomous model, nominal response model as an example. And then so based on all the model, we simulate the idealized item pool, about 600 items, and then they are cover the model parameter very well. And then in this situation, we define the relative efficiency as the ability estimator from our proposed response revision is allowed in the CAT, divided by the variance from the standard CAT where response revision is not allowed. So when we do this numerical example, again, everything follows the model. We haven't talked about the abnormal test-taking behavior. So, and we also simulate in the testness 40, students maybe revise a small number of questions, so 1 to 3, or a relatively large number of questions, 7 to 10. Again, the revised response follow our model. And then, so here let's look at the 2PL. So 2PL is a dichotomous model, so we can only investigate the equal weight. So conditional method is not applied. And then this blue line represents 1. So here we can see that the ability estimator from our proposed result, the ratio is always smaller than 1, so which means our ability estimation variance is smaller than the standard CAT where response revision is not allowed. And then if we have the nominal response model, then we can investigate the conditional estimator and equal weight. So for these two estimators, they are, the equal weight is always the best. And then conditional, for some of the ability, they are same as the CAT, but for the high ability, the efficiency is higher. So it's kind of a numerical. So this is quite expected because everything follows our model. And then how about the fresh estimator? So actually, I don't know the exact answer about asymptotic distribution for fresh, but we do some simulation study. We found that if they only revise a small number of questions, then the fresh estimator essentially just have the standard, just like the standard CAT, where response revision is not allowed. And then because the efficiency, so the memory list is like fresh, the efficiency just around 1 in the simulation study. But here, I do have to admit that if students, they revise all the responses or they keep revising back and forth, then the fresh estimator might be resulting in a very bad estimation. So that's a statistical property. And I believe some of you may think the statistical property is not that interesting because you have to assume everything follows your model. Then let's investigate in the situation where the responses does not follow our model. So in this case, this is back to our motivating example. The student, they had one careless mistake in the early stage of the test. So this black line represents the standard CAT where they don't have such mistake. So that's the best bias we can have. And then for the fresh estimator, it's actually the result is quite good. So the blue line, the yellow line here, so the fresh estimator can actually completely remove the error in this simulation study. And then for the equal weight, because it put the equal weight on the wrong and the correct response. And then they can only reduce partial error. So basically the equal weight here is not that good to reduce the measurement error. And then the second situation we consider about is, how about some students, they take some strategy. So here there are many different strategies discussed in the literature, but here we think this strategy might be a realistic strategy, actually first proposed by Kingsbury, and then the reference is not complete, so I just picked several here. So the general idea is that students, they might realize they make a mistake if they find the current item is become easier. And then I do lots of review, and then some researchers even conduct experiments, coach students to take this strategy. And actually, the general conclusion is maybe it's not that easy for students to recognize the difference of the ability of the difficulty change. But here we just treat this as a like worst case scenario. So how about if they can really judge the difference between the adjacent items? Here, so we do the simulation. We consider they can, they probably can realize the difference of the two difficulty parameter if the difference is actually smaller than x, and then they will go back to revise the previous item with probability y. So here we consider the y as like 0.73, or they can like 100%, they can recognize this difference. So this is just a scenario we consider to evaluate this three estimator. So again, here we still use that 2PL model. We actually do for the polysemous item, but maybe I don't have time. So here I just show the dichotomous item. So here, this is the result when the students, they have 75% chance to recognize the difference of the items. And then in that situation, when we simulate their revised answer, we generate the revised answer from the original IRT model. So if it is different from the initial response, then they change. If it is same, then they do not change. So in this case, then typically for students, they basically just revise 1 to 2 items on average. So in this situation, we can see that for the fresh estimator, it is had some positive bias. So it is less robust than the equal weight. And this is for a situation 100% of students, they can recognize the difference, and they basically revise more items than the first situation. Then the bias from the fresh estimator is even larger. But the equal weights, they are quite close to the standard CAT where response revision is not allowed. So in this situation, the equal weight become better. Then there is a very interesting question. So can we determine, so basically for the equal weight and fresh, we give them weight based on our model assumption. And then there is a question I'm interested to know, can we determine the weight to each response adaptively? If it is a bad response, so for example, the response not due to your latent trait, or you try to game the system, then we put less weight on it. So if the response is a good response, for example, for your revised response to revise your mistake, then we put more weight on it. To be honest, I don't know whether I can have the exact solution or not, but this is a possible solution I think we can investigate. So in general, this is kind of weighted estimation approach. This is not new. In the paper pencil test, there are several research talk about the weighted MLE method or related things. So here, basically, we want to define a residual function or residual for describe the model violation at the response J to item I. And then after we determine this residual function, then we have to find a weight function. So when the residual is small, basically 0, then we give a larger weight as 1. If the residual is very large, and then we give a weight closer to 0. And this residual function, the result is just in 0 and 1, 0 to 1. So how can we determine the residual function? This is a very, really most recent work I'm working on. So I find some like references from a paper, and then it's actually not in that paper, but in the discussion in that paper. It's very interesting. So they propose a cross-validation method. So so basically we can calculate the ratio for each responses in the test process. So here, this X bracket I represent you delete the I's response. And then here, basically, this is a likelihood based on all the responses on the current ability estimate. And this is a likelihood based on all the response except the I's one. And then this is a theta hat by deleting the I's one. And then here, this is information with a similar explanation. And then we can actually define the residual as this ratio -1, because I want to put the residual onto from 0 to 1 on the scale. That's why I subtract 1. So here I just use some numerical result to present. So for examinee theta equal to 3, so very high ability, he or she might have mistakes on 3 questions, and then they go back to correct all of them. Then we have 6 data. In this situation, by using that cross-validation methods, the ratio, like the errors for the first 3 questions, they are very low value, and then for the revised response, it's high value, and then I just subtract 1, and then it's become the residual for the bad data is really large, and for the good data is very small. Okay. So after we determine the residual, then we need to find a good weight function to do the estimation. And then here there are some Hilbert type or Tukey's bi-square weights have been explored in by some researchers. And here actually there are many probability distribution we can consider. In general, for the probability density function, we just want to put when the residual equal to 0, the weight is 1. And then when the residual is far away from 0, the weight just decreases to 0. So here I just play it around, and I choose a gamma function, and I call it as an adaptive weight method. So this green line. So now this is a green line. Revisit this careless mistake. So this green line is the performance now is between the equal weight and the fresh estimator. So again, it cannot completely reduce error because we still count their initial, but then I think the performance become better. And then how about the second situation? If they try to game the system, now the green line represent adaptive weight methods. So again, it's more robust than fresh, and it's close to the equal weight. So maybe I think this is some possible solution. So in general, we have built a statistical modeling framework for CAT with response revision, and then there are some challenges about like model mystification. I think we still need to have more work to be done related to that area. So that is my presentation. Thank you.
Those of you who need to go to the bathroom, you are free to go, but the session still continues. Do you have any questions for our third presenter?
Yeah.
I've got the one question. I'm intrigued by your results where you get the ratio of the variances, you know, that you're showing greater efficiency for new estimators. I'm trying to figure out in my head how this is happening.
Oh,
when
yeah.
you're doing this simulation, or when you're doing the revision, are you always doing the revision to change the response stream so that it's more consistent with the model?
Yeah. So when I show the numerical result, everything follows our model assumption. Yeah.
So what you're doing is you're changing responses that were sort of violating the model. They were randomly generated, but they are the furthest ones away from the model, and you're changing those to, or some of them at least, to be more consistent with the model. So that makes your estimator have a smaller standard deviation because you're having a higher consistency with the model.
Well, like when we do a simulation, we have the model to generate the response. Let's follow the IRT model. And then we also have the model to simulate the revised response. And then when we simulate the revised response, it's follow our model. It's not it's not
closer to the, you know, so let's say in the beginning, because you generated data and the item was supposed to have a probability of 0.8 of getting a correct response, but you gave it a wrong response because when you simulated the data, it came out with a 0. Now, if you go back and then now do a revision and you change that to a 1 because, you know, this is to be more consistent with the model, then you're going to get a response stream that's more consistent, which will give it a smaller standard error, and which will give you the kind of results that you get.
So you are talking about the multi-weighting example or the numerical example we support our statistic conclusion?
Right. Well, it was the one where you were showing the graph
Oh, yeah. So for that one, this one?
Yeah, here, yeah.
Okay, so for this one, I would like to explain. For when we generate the response, everything followed the IRT model. We didn't switch their response, so everything is followed the IRT model. But then when we simulated their revised response, we actually, because we have some assumption about when they will go back to revise. So once they go back to revise, their revised answer follow our assumed model. So giving their current answer is A, what's the probability for a switch to B? So if that is the newly generated answer is really that one, then they switch. If it is the same as the initial one, they don't switch. So in that situation, because I know it's my hard to understand, but in that situation, maybe because we have more data, then we have more information, everything follows the model, so that's why we have the higher efficiency there. Maybe we can discuss later. Yeah. Yeah.
Well, first of all, I'm not in favor of this review procedure.
Mm-hmm.
If the motivation is to please students, I think that's a bad motivation. Second issue should provide good measures.
Yeah. So that.
If you provide good measures to standardize the test.
Uh-huh.
You give up standardization.
Yeah, I agree. But I think so that's why also one of the motivation we want to reduce. Okay.
If you really want to please students, you should have a review second. You want a high score on those ones. And then give everyone a high score. But
Okay.
My point is, I'd like to go back to the first question. I think we have serious missing non-random problems. For instance, the FASH method. What happens conceptually if a candidate goes back to an item and
Yeah.
a response? And then based on the response, start a new solution process. But that's a different item. The item parameters change if you visit an item.
So you are talking about the item parameters.
Yeah, so it's psychometrically becomes a different item. And then you throw away the first item. So that's missing one at random.
Yeah. So.
Look at the response and then delete the item. Your method needs to be biased, especially the FASH estimator. And also the last version, the adaptive weighting, you look at the response and then put a weight on it. You should never look at the response. As soon as you start looking at the response, you run into missing response.
Yeah, actually, I think there are some challenges I haven't solved. Is if you really allow them to revise, then you have additional point for some items, and then how did you do the recalibration after you collect data? So I think that part related to some missing part there. Yeah, I do believe we have to also solve that problem in order to promote our approach. Yeah.
We're going slightly different direction. I'm not sure if I'm a fan of you, but one of the things I do know is that different individuals review differently. And so if you have Native American males, their review tendencies will be different from Native American females.
Okay.
Or,
Yeah.
Caucasian American females. So one of the things you should look at as you're going through the data is to figure out whether by doing this type of analysis you're causing dip.
So
because there could be a substantial difference in the percentage and the number of revisions for different groups of kids.
yeah.
And so it'd be useful to look at.
Yeah, that's a very good search.
Kind of boring.
Yeah, but actually that's also something I'm thinking about. Like even I think response revision is a very natural thing. Like students can decide by themselves whether they want to revise or not. So this is an option we provide there. They don't have to revise if they don't. Just like paper pencil test, everybody revise. So yeah.
But they don't.
They don't?
If you look at erasures
Okay.
differ by gender. Erasures differ by ethnic group. And so
Interesting topic before you all
Okay. Yeah. That's an interesting topic. Okay. Yeah. Okay. Well, we can discuss.
All right. Any other take our third speaker again.